Today we're diving into one of the strangest phenomena in planetary science, Superionic ice and warm ice, where water behaves in ways you never imagined. Under extreme conditions found deep inside ice giant planets, water transforms into exotic phases that challenge our everyday understanding of matter. Let's start by understanding how normal ice differs from these exotic forms. Normal ice, the kind in your freezer, forms when water molecules arrange themselves in a hexagonal crystal lattice at 0 degrees Celsius and normal pressure. Here's a simplified view of normal ice structure. Each oxygen atom is surrounded by hydrogen atoms in a rigid, organized pattern. Normal ice exists at 1 atmosphere of pressure and 0 degrees Celsius. But what happens when we subject water to the insane pressures found inside giant planets? That's where things get truly weird. Let's explore the extreme conditions inside Uranus and Neptune. Ice giant planets like Uranus and Neptune have layered structures. The middle layer contains exotic ice under tremendous pressure. The pressure in these regions reaches 2 to 6 million atmospheres, which is millions of times stronger than Earth's surface pressure. The temperature is around 5,000 Kelvin, or nearly 4,700 degrees Celsius. That's hotter than the surface of some stars. You might wonder, how can ice possibly exist at temperatures higher than a blast furnace? The answer lies in pressure. The extreme pressure forces water molecules into solid crystal structures, even at these scorching temperatures, creating what scientists call hot ice or warm ice. Now let's explore Superionic ice, one of the most unusual phases of matter ever predicted. In Superionic ice, oxygen atoms lock into a rigid crystal lattice, but hydrogen ions break free and flow through this lattice like a liquid. Here's a representation of Superionic ice. The red circles are frozen oxygen atoms in a lattice, while yellow dots represent hydrogen ions flowing freely between them. This creates a truly bizarre state of matter that is simultaneously solid and liquid, like ice with a liquid interior flowing through it. We can think of it as solid oxygen plus liquid hydrogen equals Superionic ice. The flowing hydrogen ions give Superionic ice remarkable electrical properties. Because hydrogen ions are charged particles, their flow creates electrical conductivity, making Superionic ice behave like a metallic conductor. The electrical conductivity is around 100 Siemens per centimeter, which is comparable to some metals. Imagine electric current flowing through the ice as hydrogen ions move through the oxygen lattice, creating a conducting pathway. This electrical conductivity is crucial for understanding the bizarre magnetic fields of Uranus and Neptune. The magnetic fields of Uranus and Neptune are unlike any other planets in our solar system. Most planets, like Earth, have dipole magnetic fields that align roughly with their rotation axes, like a bar magnet. Here's a normal planetary magnetic field. The field lines emerge from the poles, aligned with the planet's rotation axis. But Uranus and Neptune have highly tilted, complex, multipolar magnetic fields that are offset from their centers. The ice giants have chaotic, tilted magnetic fields shown here in red, very different from the orderly field aligned with rotation. The magnetic field of Uranus is tilted about 60 degrees from its rotation axis, which is extremely unusual. Scientists believe the flowing hydrogen ions in Superionic ice layers generate these complex, multipolar magnetic fields through electrical currents. Recently, scientists have successfully created Superionic ice in laboratory experiments. The main challenge is recreating the million atmosphere pressures and extreme temperatures found inside ice giants. Scientists use diamond anvil cells, where 2 diamonds squeeze a tiny water sample between them, creating the necessary extreme pressures. They combine diamond anvil cells with powerful laser heating to simultaneously achieve the high pressure and high temperature needed. The experiments reach about 2 million atmospheres and 5,000 Kelvin, matching conditions inside ice giants. Using X-ray diffraction, researchers confirmed the unique structure of Superionic ice with frozen oxygen and mobile hydrogen. Now let's explore an even more recent discovery, Ice XXI, a completely new form of ice. In 2024, scientists discovered Ice XXI using ultrafast compression experiments that squeeze water in just milliseconds. The compression happens in about 1 millisecond, which is 1,000th of a second, faster than you can blink. The remarkable thing about Ice XXI is that it forms at room temperature, around 20 degrees Celsius, but requires enormous pressure. Ice XXI has a previously unknown crystal structure, with water molecules arranged in a unique geometric pattern never seen before. It requires about 1 million atmospheres of pressure at room temperature of 20 degrees Celsius. You might wonder why the speed of compression matters for creating this new ice phase. Ultra-fast compression prevents water molecules from following their normal crystallization pathways, forcing them into this new exotic structure. Let's visualize how all these ice phases relate using water's phase diagram. Here's a simplified phase diagram of water. Normal ice exists at low pressure and low temperature. As we increase both, we reach Superionic ice and Ice XXI regions. Remarkably, water has at least 20 known ice phases, each with unique crystal structures and properties. Most of these exotic ice phases require extreme conditions not found naturally on Earth's surface, but common elsewhere in the universe. Let's put these extreme conditions into perspective with some numerical comparisons. The pressure inside ice giants is about 2 million atmospheres. Compare this to Earth's atmospheric pressure of just 1 atmosphere at sea level. The ice giant pressure is 2 million times greater than Earth's surface pressure. To visualize this, it's like having the weight of 2,000 elephants concentrated on a single postage stamp. Here's a visual representation showing the enormous pressure concentration, with many dots representing elephants pressing down on a tiny stamp. The temperature is around 5,000 Kelvin. For comparison, the surface of our Sun is about 5,800 Kelvin, so Superionic ice exists at temperatures approaching the Sun's surface. Yet despite this incredible heat, the material remains solid because the immense pressure overwhelms the thermal energy. Understanding exotic ice phases has profound implications for planetary science. Ice giant planets like Uranus and Neptune are actually very common throughout the universe, making up a large fraction of known exoplanets. Understanding the exotic ice in their interiors helps us explain how these planets formed, evolved, and maintain their unusual magnetic fields. Neptune definitely contains Superionic ice, while large moons like Ganymede and Titan might have small regions where it could exist. Detecting it would require detailed seismic studies or analysis of magnetic field anomalies from these bodies. Let's examine the clever experimental techniques scientists use to study these exotic phases. Dynamic compression uses powerful shock waves to compress water samples in microseconds, mimicking planetary collision processes. A projectile slams into a sample at high velocity, creating a shock wave that compresses the water to extreme pressures in microseconds. Static compression uses diamond anvils, which slowly squeeze samples while maintaining pressure for longer periods. Scientists then use X-ray diffraction to reveal the atomic scale crystal structure of the exotic ice phases. X-rays pass through the sample and diffract in patterns that reveal the arrangement of atoms, like a molecular fingerprint. Let's quantify some key properties of Superionic ice. Superionic ice has a density of about 2.5 grams per cc, which is more than twice as dense as normal ice. Compare this to normal ice, which has a density of 0.92 grams per cc and floats on water. The hydrogen diffusion coefficient is about 10 to the minus 5 square centimeters per second, indicating very mobile hydrogen ions. This means hydrogen ions zip through the oxygen lattice almost as freely as molecules in a liquid, despite the solid structure. The oxygen atoms form a rigid grid, while hydrogen ions flow freely through the channels, creating this dual solid-liquid behavior. The timescales for forming these exotic ices are fascinating. Normal ice takes seconds to minutes to crystallize from liquid water in your freezer. The formation time for normal ice is typically 10 to 100 seconds. But Superionic ice forms in just microseconds when subjected to shockwave compression. The formation time is 1 to 10 microseconds, which is a millionth of a second. Ice XXI forms in milliseconds with ultra-fast compression techniques. The formation happens in about 1 millisecond, or 1,000th of a second. Here's a comparison showing relative formation speeds. Ice 21 forms fastest, then Superionic ice, with normal ice being slowest. Let's explore the energy involved in creating these exotic phases. The compression energy needed is about 100 kilojoules per mole of water. Compare this to melting normal ice, which requires just 6 kilojoules per mole, about 16 times less energy. The ratio of compression energy to melting energy is about 16, showing how much more energy these exotic phases require. This chart shows the dramatic difference in energy requirements. Creating Superionic ice requires far more energy than simply melting normal ice. In actual planets, this enormous energy comes from gravitational compression, as the planet's mass squeezes the interior. An interesting question: could Superionic ice exist in other places besides ice giants? It might exist deep inside large icy moons like Ganymede or Titan, where pressures could reach necessary levels. The body needs sufficient mass to generate the gravitational pressure required, limiting it to large objects. Rough estimates suggest objects need more than 0.1 Earth masses to create these conditions in their interiors. Neptune definitely contains Superionic ice, while large moons like Ganymede and Titan might have small regions where it could exist. Detecting it would require detailed seismic studies or analysis of magnetic field anomalies from these bodies. Let's understand exactly how Ice 21 forms through ultrafast compression. First, pressure increases extremely rapidly, in less than a millisecond, giving molecules no time to find their normal arrangement. Water molecules freeze in place before they can rearrange into familiar ice structures. This traps them in a completely novel crystal structure that wouldn't form under slow compression. Here we see the transition from disordered liquid water on the left to the ordered Ice 21 crystal structure on the right. The pressure increase rate must exceed 10 to the 9th atmospheres per second to create Ice 21. That's like going from normal pressure to the pressure at the deepest ocean trench in the blink of an eye. Let's summarize what we've learned about exotic ice phases and their importance in understanding our universe. Exotic ice phases show us the incredible diversity of water under extreme conditions, challenging our everyday understanding of matter. These exotic ices not only expand our knowledge of water, but also help us understand the interiors of ice giants and potentially other icy bodies in our solar system. By studying these exotic ice phases, we gain insights into the formation and evolution of planets, moons, and the solar system itself. The study of exotic ice is an active and exciting field, with new discoveries continually expanding our understanding of these mysterious and fascinating materials.